Fundamentals of Cooling 1. For best viewing results, we recommend that you maximize your browser window now. The screen controls allow you to navigate through the e-learning experience. Using your browser controls may disrupt the normal play of the course. Click the Notes tab to read a transcript of the narration. At the completion of this course, you will be able to explain why cooling in the data center is so critical to high availability, distinguish between precision and comfort cooling, recognize how heat is generated and transferred, define basic terms like pressure, volume, and temperature, as well as their units of measurement, describe how these terms are related to the refrigeration cycle, and describe the refrigeration cycle and its components. Every information technology professional who is involved with the operation of computing equipment needs to understand the function of air conditioning in the data center or network room. This course explains the function of basic components of an air conditioning system for a computer room. Whenever electrical power is being consumed in an information technology room or data center, heat is being generated. We will talk more about how heat is generated a little later in this course. In the data center environment, heat has the potential to create significant downtime and therefore must be removed from the space. Data center and IT room heat removal is one of the most essential, yet least understood, of all critical IT environment processes. Improper or inadequate cooling significantly detracts from the lifespan and availability of IT equipment. A general understanding of the fundamental principles of air conditioning and the basic arrangement of precision cooling systems facilitates more precise communication among IT and cooling professionals when specifying, operating, or maintaining a cooling solution. The purpose of precision air conditioning equipment is the precise control of both temperature and humidity. Despite revolutionary changes in IT technology and products over the past decades, the design of cooling infrastructure for data centers had changed very little since 1965. Although IT equipment has always required cooling, the requirements of today's IT systems, combined with the way that those IT systems are deployed, has created the need for new cooling-related systems and strategies, which were not foreseen when the cooling principles for the modern data center were developed over 30 years ago. Today's require precise, stable environments in order for sensitive electronics to operate at their peak. IT hardware produces an unusual, concentrated heat load and at the same time is very sensitive to changes in temperature or humidity. Most buildings are equipped with comfort air conditioning units, which are designed for the comfort of people. When compared to computer room air conditioning systems, comfort systems typically remove an unacceptable amount of moisture from the space and generally do not have the capability to maintain the temperature and humidity parameters specified for IT rooms and data centers. Precision air systems are designed for close temperature and humidity control. They provide year-round operation with the ease of service, system flexibility, and redundancy necessary to keep the technology room up and running. As damaging as the wrong ambient conditions can be, rapid temperature swings can also have a negative effect on hardware operation. This is one of the reasons hardware is left powered up, even when not processing data. According to ASHRAE, the recommended upper limit temperature for data center environments is 81 degrees Fahrenheit or 27.22 degrees Celsius. Precision air conditioning is designed to constantly maintain temperature within 1 degree Fahrenheit or 0.56 degrees Celsius. In contrast, comfort systems are unable to provide such precise temperature and humidity controls. A poorly maintained technology room environment will have a negative impact on data processing and storage operations. A high or low ambient temperature or rapid temperature swings can corrupt data processing and shut down an entire system. Temperature variations can alter the electrical and physical characteristics of electronic chips and other board components, causing faulty operation or failure. These problems may be transient or may last for days. Transient problems can be very hard to diagnose. High humidity can result in tape and surface deterioration, condensation, corrosion, paper handling problems, and gold and silver migration leading to component and board failure. Low humidity increases the possibility of static electric discharges. Such static discharges can corrupt data and damage hardware. Now that we know that heat threatens the availability of IT equipment, it's important to understand the physics of cooling and define some basic terminology. First of all, what is heat? Heat is simply a form of energy that is transferred by a difference in temperature. It exists in all matter on Earth in varied quantities and intensities. Heat energy can be measured relative to any reference temperature, body, or environment. What is temperature? Temperature is most commonly thought of as how hot or cold something is. It is a measure of heat intensity based on 3 different scales: Celsius, Fahrenheit, and Kelvin. What is pressure? Pressure is a basic physical property of gas. It is measured as the force exerted by the gas per unit area on its surroundings. What is volume? Volume is the amount of space taken up by matter. The example of a balloon illustrates the relationship between pressure and volume. As the pressure inside the balloon gets greater than the pressure outside of the balloon will get larger. Therefore, as the pressure increases, the volume increases. We will talk more about the relationship between pressure, volume, and temperature a little later in this course. Now that we know the key terms related to the physics of cooling, we can now explore the 3 properties of heat energy. A unique property of heat energy is that it can only flow in one direction, from hot to cold. For example, if an ice cube is placed on a hot surface, it cannot drop in temperature. It can only gain heat energy and rise in temperature, thereby causing it to melt. A second property of heat transfer is that heat energy cannot be destroyed. The third property is that heat energy can be transferred from one object to another object. In considering the ice cube placed on a hot surface again, the heat from the surface is not destroyed. Rather, it is transferred to the ice cube, which causes it to melt. There are 3 methods of heat transfer: conduction, convection, and radiation. Conduction is the process of transferring heat through a solid material. Some substances conduct heat more easily than others. Solids are better conductors than liquids, and liquids are better conductors than gases. Metals are very good conductors of heat, while air is a very poor conductor of heat. Convection is the result of transferring heat through the movement of a liquid or gas. Radiation related to heat transfer is the process of transferring heat by means of electromagnetic waves emitted due to the temperature difference between 2 objects. For example, blacktop pavement gets hot from radiation heat by the sun's rays. The light that warms the blacktop from the sun is a form of electromagnetic radiation. Radiation is a method of heat transfer that does not rely on any contact between the heat source and the heated object. If you step barefoot on the pavement feels hot. This feeling is due to the warmth of the pavement being transferred to your cold feet by means of conduction. The conduction occurs when 2 objects at different temperatures are in contact with each other. Heat flows from the warmer to the cooler object until they are both the same temperature. Finally, if you look down a road of paved blacktop, in the distance you may see wavy lines emanating from the top of the road, much like a mirage. This visible form of convection is caused by the transfer of heat from the surface of the blacktop to the cooler air above. Convection occurs when warmer areas of a liquid or gas rise to cooler areas in the liquid or gas. As this happens, cooler liquid or gas takes the place of the warmer areas which have risen higher. This cycle results in a continuous circulation pattern, and the heat is transferred to cooler areas. Hot air rises and cool air falls to take its place. This is a description of convection in our atmosphere. As mentioned earlier, heat energy can only flow from hot to cold. For this reason, we have air conditioners and refrigerators. They use electrical or mechanical energy to pump heat energy from one place to another, and are even capable of pumping heat from a cooler space to a warmer space. The ability to pump heat to the outdoors, even when it is hotter outside than it is in the data center, is a critical function that allows high-power computing equipment to operate in an enclosed space. Understanding how this is possible is the foundation to understanding the design and operation of cooling systems for IT installations. Wherever electrical power is being consumed in an information technology room or data center, heat is being generated that needs to be removed from the space. This heat generation occurs at various levels throughout the data center, including the chip level, server level, rack level, and room level. With few exceptions, over 99% of the electricity used to power IT equipment is converted into heat. Unless the excess heat energy is removed, the room temperature will rise until IT equipment shuts down or potentially even fails. Let's take a closer look at heat generation at the server level. Approximately 50% of the heat energy released by servers originates in the microprocessor. A fan moves a stream of cold air across the chip assembly. The server or rack-mounted blade assembly containing the microprocessors usually draws out cold air into the front of the chassis and exhausts it out of the rear. The amount of heat generated by servers is on a rising trend. A single blade server chassis can release 4 kilowatts or more of heat energy into the IT room or data center. Such a heat output is equivalent to the heat released by 40 100-watt light bulbs, and is actually more heat energy than the capacity of the heating element in many residential cooking ovens. Now that we have learned about the physics and properties of heat, we will talk next about the ideal gas law. Previously, we defined pressure, temperature, and volume. Further, it is imperative to the understanding of data center cooling to recognize how these terms relate to each other. The relation between pressure, volume, and temperature is known as the ideal gas law, which states PV over T equals constant. In this equation, P is pressure of gas, V is the volume occupied, and T is the temperature. In simpler terms, if pressure is constant, an increase in temperature results in a proportional increase in volume. If volume is constant, an increase in temperature results in a proportional increase in pressure. Inversely, if volume is decreased and pressure remains constant, the temperature must decrease. Basically, pressure and volume are directly proportional to temperature and inversely proportional to each other. Pressure and temperature are both controlled by the ideal gas law. However, because the volume is not held constant, that is, the atmosphere can expand and contract, the relationships between pressure and temperature are complex. Temperature decreases linearly with increasing altitude, whereas pressure decreases exponentially. For example, you may have experienced the outside of an aerosol can becoming colder as you spray it. This is because the can is a fixed volume, and as the pressure within the can decreases as it is sprayed, the temperature also decreases, causing the can to feel cold. The refrigeration cycle is a closed cycle of evaporation, compression, condensation, and expansion that has the net effect of moving heat energy away from an environment and into another environment, in this case from inside the data center to the outdoors. The working fluid used in the refrigeration cycle is known as the refrigerant. Modern systems primarily use fluorinated hydrocarbons that are non-flammable, non-corrosive, non-toxic, and non-explosive. Refrigerants are commonly referred to by their ASHRAE numerical designation. Environmental concerns of ozone depletion may lead to legislation increasing or requiring the use of alternate refrigerants like R134A. Additional legislation related to the use of alternate refrigerants is under consideration. Refrigerant changes its physical state from liquid to gas and back to liquid again each time it traverses the various components of the refrigeration cycle. As the refrigerant changes state from liquid to gas, heat energy flows into the refrigerant from the area to be cooled, the IT environment, for example. Conversely, as the refrigerant changes state from gas to liquid, heat energy flows away from the refrigerant to a different environment, outdoors or to a water source. Evaporation is the first step in removing heat energy from a computer room and is the first step in the refrigeration cycle. The evaporator coil acts as an automobile radiator operating in reverse. Warm air from the computer room is blown across the evaporator coil by a fan, while the tubes comprising the coil are supplied with the refrigerant exiting the expansion valve. When the warm computer air passes through the cold evaporator coil, it is cooled, and this cool air is delivered back to the computer room. Even though the evaporator coil is cold, at approximately 46 degrees Fahrenheit or 7.8 degrees Celsius, the refrigerant inside is evaporating or boiling, changing from liquid to a gaseous state. It is the heat from the computer room that is boiling the refrigerant, passing heat energy to the refrigerant in the process. The refrigerant at this point is a cool gas in a small pipe that is carrying the heat energy away from the computer room. Compression is the next step in removing heat energy from a computer room. The vaporized but cool refrigerant carrying the heat from the data center is drawn into a compressor. This compressor has two important functions. It pushes the refrigerant carrying the heat energy around the refrigeration loop. It compresses the gaseous refrigerant from the evaporator coil over 200 psi. It is a fundamental property of gases that the compression of a gas causes its measured temperature to rise. Therefore, the moving gaseous refrigerant exiting the compressor is hot, over 125 degrees Fahrenheit or 52 degrees Celsius, as well as compressed. This temperature rise, due to compression, is the key to the ability of the refrigeration cycle to eject heat into the outdoor environment. The next stage of the refrigeration cycle is condensation. In this stage, hot compressed refrigerant carries the computer room heat energy from the compressor to the condenser coil. The coil is made of small tubes coiled up into a block of metal fins and resembles an automobile radiator. This coil transfers heat to the air and operates at a temperature higher than the air. This means that the air flowing across the coil is heated by the coil, and that the hot gaseous refrigerant flowing through the coil is conversely cooled. Heat is flowing from the refrigerant to the air. The air is typically blown across the hot coil by a fan, which exhausts the hot air to the outdoors. In this way, the heat energy from the computer room has been transferred to the outdoors. The condenser coil acts like the radiator in a car, in that it carries heat from the engine to the air outside the car. In the next stage, the expansion stage, the refrigerant exits the condenser coil as a high-pressured liquid, although at a lower temperature. The refrigerant then passes through an expansion valve, which has two key functions that are critical to the refrigeration cycle. It precisely regulates the flow of high-pressure refrigerant at a rate that maintains an optimal difference in pressure to ensure efficient cooling. Secondly, the refrigerant escapes the expansion valve as a cooled refrigerant. Once this cooled refrigerant has passed through the evaporator coil, it is changed to a gas. This is because the boiling point of the liquid refrigerant is extremely low. Therefore, as the warm air from the computer room blows across the coils of the evaporator, the refrigerant that enters the coil gets heated and starts boiling. Thus, it changes to a gas. In this way, the cold refrigerant absorbs the heat energy from the air and carries it away from the data center. At this stage, the refrigeration cycle is repeated, and the net result of the process is that heat is continuously flowing into the evaporator coil and continuously flowing out of the condenser coil. To summarize, let's review some of the information that we have covered throughout this course. When IT equipment is operating, heat is generated, and the removal of this heat is critical to the proper functioning of the data center environment. Precision cooling systems are required to provide adequate cooling conditions for IT spaces. Heat, pressure, temperature, and volume are interrelated for gases. Heat is transferred via conduction, convection, and radiation, and it only moves naturally from areas of high heat to areas of low heat. The refrigeration cycle is a closed cycle of evaporation, compression, condensation, and expansion that serves to remove heat from the data center.